Supersonic travel could be especially important for industries involved in medical transportation and disaster relief.
Imagine getting to London in 3 hours.
As Brian mentioned, when you go hypersonic, or in this case, a Mach 3, you have a lot of heat.
This is the story of an aircraft engine that shouldn't work, a speed record that's stood unchallenged for over 2 decades, and a startup that just hit $1 billion valuation, trying to do what the entire U.S. aerospace establishment has failed to accomplish since 2004. We're talking about hypersonic flight, Mach 5 and beyond, where the air itself becomes your enemy, where surface temperatures climb high enough to melt titanium, and where scramjet combustion has to happen in a fraction of a millisecond, or the whole thing falls apart. On November 16, 2004, a small, unmanned, wedge-shaped aircraft called the X-43A screamed through the atmosphere at Mach 9.6. That's nearly 6,400 miles per hour, nearly 2 miles every second. At an altitude of 33,500 meters, it became the fastest air-breathing aircraft ever flown. And here's what makes that fact extraordinary. 22 years later, nothing has beaten it. Not a single air-breathing aircraft has gone faster. The record still stands. But the X-43A's engine only ran for about 10 seconds. 10 seconds of powered flight. That was enough to generate critical data on stability and aerodynamic performance at hypersonic speeds, but it wasn't enough to build a program on. The United States had cracked open the door to a new era of aviation, peeked through, and then walked away. To understand why that happened and why it matters now, you need to understand what makes hypersonic flight so brutally, almost absurdly, difficult. Let's start with the engine. A scramjet, which stands for supersonic combustion ramjet, appears elegantly simple in concept. It has no moving parts, no spinning turbine blades, no compressors, no fans. Instead, it uses the vehicle's own forward velocity to ram air into the engine at tremendous pressure. Fuel gets injected into that compressed airstream. It ignites, and the expanding gases produce thrust. Beautiful in theory, nightmarish in practice. Here's the problem. In a conventional jet engine, incoming air gets slowed down to subsonic speeds before combustion. That gives you time. Time to mix fuel. Time to ignite, time to sustain a stable flame. A scramjet doesn't have that luxury. The air passing through the engine is still traveling at supersonic speeds. Combustion has to happen in a fraction of a millisecond. If you slow the air down too much, you lose efficiency and generate catastrophic heat. If you don't slow it down enough, the fuel can't ignite. You're trying to light a match in a hurricane, except the hurricane is moving at 5 times the speed of sound, and everything around you is hot enough to glow white. And that brings us to the thermal barrier, which is really where conventional wisdom said this whole endeavor was impossible. The surface temperature of an aircraft flying at Mach 5 reaches as high as 3,500 degrees Fahrenheit. That's hot enough to melt titanium, one of the strongest aerospace materials we have. Push beyond Mach 5, and temperatures within the shock layer surrounding the aircraft can exceed 10,000 degrees. At the vehicle's surface, recorded temperatures have reached around 2,500 degrees Celsius. At those temperatures, the air itself begins to dissociate. Molecules break apart. The physics change. You're no longer just dealing with aerodynamics. You're dealing with plasma dynamics, chemical reactions in the airflow, thermal loads that can warp or destroy any known material in seconds. Dr. Kevin Bowcutt, Boeing's Senior Technical Fellow and Chief Scientist of Hypersonics, put it this way. It took about 50 years to develop scramjet technology to the point it could be demonstrated in flight. It took so long because of the extreme thermal environment encountered at hypersonic speeds and the challenges of ground testing at hypersonic speed due to high flow energy and temperature. Hypersonic flow physics are also difficult to analyze theoretically or simulate in computers. 50 years, half a century of engineering to get 10 seconds of powered flight. And after the X-43A splashed into the Pacific, the momentum just stalled. This is what people in the defense community now call the lost decades. The United States had a genuine chance to build on the X-43A's success, to turn that tiny wedge of experimental data into a sustained lead in air-breathing hypersonics. The Air Force's X-51 Waiver Rider program did achieve a 240-second scramjet burn in 2013, 24 times longer than the X-43A, but like its predecessor, never transitioned to an operational program. Instead, the U.S. let the technology languish. NASA's Hyper-X program, which cost $230 million over 8 years, was considered a success. But there was no follow-on, no production program, no sustained investment in turning the technology into something operational. Meanwhile, the rest of the world was watching. China unveiled the CJ-1000 in 2025, a scramjet-powered hypersonic missile with a range of 6,000 kilometers and speeds exceeding Mach 6. Russia fielded the ship-launched 3M-22 Zircon missile, capable of Mach 9. China and Russia are currently the only countries known to possess operational land-based scramjet-powered hypersonic missiles, the technology the United States pioneered, other nations weaponized. Today's hypersonic arms race is happening in the shadow of choices made 20 years ago. And that shadow is exactly where a company called Hermeus stepped in. Hermeus Corporation was founded in 2018 in Atlanta, Georgia. Their CEO and co-founder, AJ Piplika, had a vision that sounded either audacious or delusional, depending on who you asked. Build a reusable hypersonic aircraft. Not a missile, not a one-shot demonstrator. An aircraft that could take off, fly at Mach 5 and beyond, and land to fly again. The core technical challenge they needed to solve is something the aerospace industry has wrestled with for decades. It's called the Mach gap. Conventional turbojet engines top out at around Mach 2.2. Scramjets don't even begin to work until about Mach 4. That leaves a dead zone between Mach 2.2 and Mach 4, where neither engine type functions well. How do you accelerate through a speed regime where your engine doesn't work? Hermeus's answer is the Chimera engine. And the name is perfect, because this thing is a hybrid beast. The Chimera operates as a turbine-based combined cycle engine, or TBCC. It functions as a conventional gas turbine at lower speeds, then transitions to a ramjet for higher speeds. Think of it as two engines fused into one airframe, sharing components, handing off thrust as the aircraft accelerates through different speed regimes. At takeoff and subsonic speeds, the turbine does the work. As velocity builds, the ramjet takes over. But here's where it gets clever. The Chimera has a precooler that reduces the temperature of the air entering the turbojet section, similar in concept to reaction engine's Sabre approach. This allows Hermeus to squeeze extra performance out of the turbine engine, pushing it to higher speeds before the ramjet transition occurs. That narrows the Mach gap. It doesn't eliminate it entirely, but it makes the handoff between propulsion modes more manageable. About 15% of the Chimera engine is 3D printed, which is part of how Hermeus developed it so fast. The company spent $18 million over 21 months to build and test the engine. In November 2022, they conducted a simulated hypersonic flight test at the Notre Dame Turbomachinery Laboratory in Indiana, and the Chimera successfully transitioned from turbojet mode to ramjet mode. That was a milestone moment, not in a wind tunnel, not in a computer simulation, in an actual engine test. The vehicle carrying this technology is called Quarterhorse, and the development timeline is almost as impressive as the engine itself. Quarterhorse Mark I went from clean sheet design to flight ready in a little over a year. On May 21, 2025, the Mark I flew for the first time at Edwards Air Force Base in California, remotely piloted. Then came the Mark 2.1, which represents a massive step up. It's comparable in size to an F-16 fighter jet, powered by a Pratt & Whitney F-100 engine, the same power plant that drives America's frontline fighters. It's nearly 3 times larger and 4 times heavier than the Mark 1, making it one of the largest unmanned aircraft ever built. On February 27, 2026, the Quarterhorse Mark 2.1 took its maiden flight, remotely piloted from Hermeus's ground-based flight deck over White Sands Missile Range airspace. 2 weeks later, the FAA issued a special airworthiness certificate in the experimental category, and on April 9th, cleared Hermeus to perform up to 7 supersonic flights through the end of 2026. All flights take place in restricted military airspace at altitudes above 30,000 feet. Jay Wageman, Hermeus's Director of Mission Operations, helped oversee the flights from Spaceport America in New Mexico. Scott McLaughlin, the Executive Director of the New Mexico Spaceport Authority, supported the operations on the ground. But Quarterhorse Mark 2.1 isn't the end state, it's the beginning. Within the Mark II series, Hermeus plans to build 3 variants, each pushing closer to the Mach 5 threshold. The Mark 2.1 will break the supersonic barrier. The successor, Mark 2.2, will push into higher Mach speeds and is expected to become the fastest unmanned aircraft in the world. The goal for the overall Mark II iteration is to reach Mach 2.5, and then comes Mark III, which is where Hermeus intends to finally cross the hypersonic barrier at Mach 5. Hermeus isn't alone in this race. Stratolaunch achieved Mach 5 with its reusable Talon A in 2024, though that design requires a carrier aircraft for launch rather than taking off from a runway like Quarterhorse. This is what the company calls hardware richness, a philosophy of building multiple prototypes in quick succession, taking well-managed technical risk, and learning through iteration rather than endless simulation. 1 aircraft per year, each one faster, each one teaching the engineers something new. Piplica put it bluntly, we're building and flying aircraft on timelines that match the urgency of the world we're in. The money is following the momentum. In March 2022, Hermeus raised $100 million in a Series B round led by Sam Altman, the same Sam Altman now running OpenAI. In 2021, the U.S. Air Force put up $60 million. And in April 2026, Hermeus closed a $350 million Series C round led by Khosla Ventures, pushing the company's valuation to $1 billion and its total raised capital past $500 million. The investor list reads like a who's who of Silicon Valley and defense innovation. Founders Fund, In-Q-Tel, which is the CIA's venture arm, RTX Ventures, Cox Enterprises, and the Georgia Tech Foundation, among others. Vinod Khosla, the venture capital legend who led the round, said, "We've been believers in Hermeus from the start. The team is on a clear trajectory to solve a critical capability gap for their customers by building, flying, and iterating at a pace that matches the modern battlefield." Major General Scott Kane, commander of the Air Force Test Center, echoed the sentiment. The promise of routine hypersonic flight is an exciting capability for the joint team. And Hermeus isn't operating in a vacuum. The broader U.S. hypersonic ecosystem is surging. The fiscal year 2026 budget requests $3.09 billion for hypersonic weapons development. The Air Force alone is asking for $802.8 million for the Hypersonic Attack Cruise Missile Program, known as HACM, with Raytheon as the prime contractor under a $985 million contract. DARPA's Secretive Aerospace Projects Office announced in February 2025 that it's developing a large hypersonic bomber prototype under the Next Generation Responsive Strike Program, aiming for a prototype by 2030. and DARPA is also kicking off a $40 million effort to develop a high Mach gas turbine engine designed for sustained air-breathing propulsion at Mach 4 and beyond. Then there's the ghost in the machine, the SR-72, sometimes called the Son of Blackbird. Lockheed Martin's Skunk Works has worked with Aerojet Rocketdyne since 2006 on a hypersonic successor to the legendary SR-71 Blackbird, which held the speed record at Mach 3.3 before its retirement in 1998. The SR-72 remains deeply classified, but its existence points to a parallel track of development happening behind closed doors. Now, let's be honest about the challenges that remain, because there are plenty of skeptics, and they aren't wrong to be cautious. The Congressional Research Service has noted that first-generation hypersonic weapons, while technically achieving the high speeds they're designed for, will likely lack sophistication. Targeting and tracking remain massive problems. First-generation hypersonic missiles aren't expected to have the accuracy or sensors needed to operate effectively against moving targets. The thermal protection problem hasn't been fully solved either. Ablative thermal protection systems, the most mature technology, were conceived in the 1960s. They work by sacrificing material, literally burning away layers to absorb heat. But if you want reusability, maneuverability, and cost-effectiveness, ablation is a dead end. Carbon-carbon composites and ceramic matrix composites are promising candidates, but materials science still has to catch up with the ambitions of the engineers. And there's the cautionary tale of the X-15, the rocket-powered aircraft that Air Force pilot Pete Knight flew to Mach 6.7 back in 1967. The X-15 never entered service. It was wildly impractical, launched from the wing of a B-52 bomber, burning through its fuel in less than 2 minutes before becoming an expensive glider. Speed alone doesn't equal capability. The vehicle has to be useful. But here's what's different this time. The X-43A was a government program operating on government timelines. Hermeus is a startup operating on startup timelines, with $1 billion in backing and a philosophy that values building over studying. They're not trying to solve every problem before they fly. They're flying to find the problems. Every flight generates data. Every data point informs the next design. MK 2.1 leads to MK 2.2 leads to MK 2.3 leads to MK 3. And MK 3 is where the hypersonic barrier finally breaks. A J. Piplica captured the company's mentality perfectly. Speed is life for us. This new funding lets us build multiple aircraft at the same time and scale our manufacturing capabilities, adding more hardware richness and robustness to our program. That accelerates our path to ramjet-powered flight. Think about where we are right now. In 2004, the fastest air-breathing aircraft ever built operated for 10 seconds and vanished into the ocean. 22 years later, a company that didn't exist until 2018 is flying F-16-sized unmanned aircraft over the New Mexico desert, cleared by the FAA for supersonic flight, and building toward Mach 5 with a combined cycle engine that transitions from turbine to ramjet in a single continuous acceleration. The United States spent 2 decades watching its hypersonic lead evaporate, while China and Russia fielded operational weapons. Now, the race to close that gap involves not just the Pentagon and DARPA, but venture-backed startups moving at Silicon Valley speed with defense-grade ambition. The record set by the X-43A still stands. Mach 9.6, nearly 2 miles per second, 22 years and counting. But for the first time in a long time, there's a credible path to not just matching that record, but making hypersonic flight routine. The question is no longer whether it's possible. We proved that in 2004. The question is whether we can do it again, and this time, whether we can make it last longer than 10 seconds.